and welcome to all in the lecture series of functional analysis. Now in this lecture we see about the bounded linear operator. So firstly we see the definition. The definition is, let capital X and capital Y be the norm spaces. Capital T from script d of t to y a linear operator where script d of t is a subset of capital X. The operator capital T is said to be bounded if there is a real number C such that for all x belongs to dt, norm of Tx it is less than or equals to C into norm of x. This is the definition of the bounded linear operator. Here we have to given the linear operator which is from a norm space x to the norm space y, and script d of t it is a subset of capital X. Now we say that the operator capital T is said to be bounded if there exists a real number C such that for all x belongs to dt, norm of Tx that is less than or equals to norm of x. Now here the norm of Tx, as T is the mapping from script d of t to capital Y, and here small dt, that means small x is the element of dt, implies that Tx, that is the image of the point x under the operator t, that is Tx. Now Tx is the element of y. As here we have to given that x and y are the norm spaces, and therefore here we are writing norm of Tx. Then in this case this is the norm on capital Y, and here we are taking C into norm of x. Now x is the element of dt, dt is a subset of capital X, and capital X is a norm space, and therefore it is the norm on capital X. But for simplicity, to avoid the confusion, we write both the norms in the same symbol, that is norm, and therefore here the operator T is said to be bounded if there is a real number C such that for all x belongs to dt, norm of Tx that is less than or equals to C into norm of x. This is the required condition for the bounded linear operator. Now here we find out the smallest possible value of C satisfying the equation 1. For this here, now we are taking the for all x belongs to dt with x not equals to 0. When x is not equals to 0, this implies that norm of x that is also not equals to 0. As norm of x not equals to 0, so we divide on both sides of the equation 1 by norm of x, and we are getting here the value norm of Tx divided by norm of x. This is lesser than or equals to C, and it is true for all x belongs to dt with the condition that x must be not equals to 0, and therefore C must be at least as bigger as the supremum of all these value, and therefore we can take C equals to the supremum of all norm of Tx divided by norm of x, with the condition that x is the element of dt, that is x belongs to dt, and x not equals to 0. This is also written as supremum over x belongs to dt minus x belongs to dt minus singleton 0 norm of Tx divided by norm of x. And this is the value of C. Now this term is also written as, it is written as norm of T. Now this is called as a norm of the operator capital T. This is the value of, and therefore we write down that norm of T it is equals to supremum over x belongs to dt, x not equals to 0, norm of Tx divided by norm of x, that is the norm of T. Now here for script d of t equals to 0, in this case norm of t that is also equals to 0, because here t0 it is always equals to 0, and therefore t it is equals to 0, and as t equals to 0 implies that norm of t equals to 0, and hence we are getting the value of norm of t. Therefore, and norm of t that is equals to this, and we know that this norm of t it is equals to c, and therefore now we are putting this value of c that is equals to norm of t in equation 1. We get that norm of tx it is less than or equals to norm of t into norm of x for all x belongs to dt. Now this is the condition for the linear operator to be boundedness. Now after this we have the lemma about the bounded linear operator. Statement of the lemma is, let capital X and capital Y be norm spaces and capital T from script d of t to y a bounded linear operator where script d of t is a subset of capital X. Then we have to show that an alternative formula for the norm of t is norm of t equals to supremum over x belongs to dt, norm of x equals to 1 norm of tx, and the another, the norm defined by norm of t equals to the supremum over x belongs to dt, x not equals to 0, norm of tx divided by norm of x satisfies n1 to n4. That means the norm defined like this satisfy all the axioms of a norm. In this way we have to prove these two statements. So firstly we prove the first one, that the alternative formula for the norm of t is norm of t equals to supremum over x belongs to dt, norm of x equals to 1 norm of t. That is we have to prove. So in the proof, given capital T from script d of t to y is a bounded linear operator. It is a bounded linear operator, and therefore for all x belongs to dt we can write down norm of tx that is less than or equals to norm of t into norm of x, where norm of t that is equals to supremum over x belongs to dt, x not equals to 0, norm of tx divided by norm of x. Now we give it the equation number 1. Now we put norm of x equals to a. As we know that norm is a real valued function, and therefore here when we are taking the norm of x, that means it is something a real number, and therefore here we put norm of x equals to a and set y equals to 1 by a into x. Y equals to 1 by a into x. Here we are taking x that is not equals to 0, and therefore norm of x that is also not equals to 0, and therefore we set y equals to 1 by a. This a is not equals to 0. Y equals to 1 by a into x. Then for x not equals to 0, then norm of y that is equals to, putting the value of y that is equals to 1 by a into x. 1 by a into x. Now 1 by a is a scalar, and therefore here norm of 1 by a into x that is equals to 1 by a into norm of x. Putting the value of a that is equals to 1 by norm of x into norm of x, and therefore here we get the value of norm of y equals to 1. Now the value of norm of y equals to 1, and therefore we put this value in equation 1. We get norm of t that is equals to supremum over x belongs to dt, x not equals to 0, norm of tx divided by norm of x. Now here we put this value, that is equals to now the value of 1 divided by norm of x, that is the norm of tx divided by the value of norm of x is a. This is equals to supremum x belongs to script d of t, x not equals to 0, 1 by a into norm of tx. As 1 by a, it is a scalar into norm of x, and for the norm we know the property of the norm is that norm of alpha x, that is always equals to mod alpha into norm of x, and here we know that a, this is nothing but the norm of x, and this x, it is not equals to 0, and therefore this a, it is always greater than 0, and therefore mod of a, it is equals to a, and we use it, and therefore here 1 by a into norm of tx, this is written as norm of 1 by a into tx. Here we may take 1 by a, that is equals to mod alpha into norm of tx, it is equals to norm of 1 by a into tx, and therefore we can write down that is equals to supremum over x belongs to dt, x not equals to 0, norm of 1 by a into tx. Now here t is linear and 1 by a is a scalar, and for the linearity we know that alpha into tx, that is equals to t of alpha x. We use this the property of the linearity here, and we can write down it is equals to supremum over x belongs to dt, x not equals to 0, norm of t of 1 by a into x. Now 1 by a into x, this is equals to y, and therefore we can write down it is equals to supremum of norm of ty. But here x is the element of dt in the same way, and we know that dt is a dt, it is a subset of x. X is a vector space, dt is also a vector space. Therefore 1 by a into x, that is also the element of dt. That means here we may write it as y belongs to dt, and here x not equals to 0, but for the y, here we have the condition that norm of y equals to 1. That means here we are getting that supremum over y belongs to dt, norm of y equals to 1, norm of ty. Now we are writing x for y, and we get it as supremum over x belongs to dt, norm of x equals to 1, norm of tx. In this way we get that norm of t, that is equals to supremum over x belongs to dt, norm of x equals to 1, norm of tx. This is the alternative formula for the norm of t. The first formula for the norm of t is that supremum over x belongs to dt, x not equals to 0, norm of tx divided by norm of x. That is the first formula, and the alternative formula is that supremum over x belongs to dt, norm of x equals to 1, norm of tx. In this way we get the two formula for the norm of t. Now in the second statement we have to show that the norm of t defined like this. Norm of t defined like this: supremum over x belongs to dt, x not equals to 0, norm of tx divided by norm of x, satisfy all the axioms of a norm. That is we have to show. So firstly we see all the axioms of a norm. So the first axiom of a norm, that is n1, it is that norm of x, it is always greater than or equals to 0. The second property of a norm is norm of x equals to 0 if and only if x equals to 0. That is the second axiom. Third axiom for the norm is norm of alpha x, it is equals to mod alpha into norm of x, where alpha be any scalar. And the fourth property of a norm, that is norm of x plus y, it is always lesser than or equals to norm of x plus norm of y. These are the four axioms of a norm. And as here we have to given that capital X and capital Y be the norm spaces. That means here for any element x belongs to capital X, satisfy all these four axioms. In the same way as here we have the mapping, that the mapping T which is from script d of t to y, and therefore for any x belongs to dt, Tx is the element of y and y is a norm space. Therefore norm of Tx also satisfy all the four axioms of a norm. So with the help of these two conditions, that x and y are the norm spaces and therefore they satisfy all the four axioms of a norm, we prove that the norm of T defined like this satisfy all these four axioms. So first we have to show that norm of T, it is greater than or equals to 0. That means we have to prove the first axiom of a norm. Now to prove this first axiom, by definition norm of T, that is equals to supremum over x belongs to dt, x not equals to 0, norm of Tx divided by norm of x. Now here we have to given that x is not equals to 0 implies that norm of x, it is strictly greater than 0, because norm of x, it is always greater than or equals to 0, but when x is not equals to 0, this norm must be strictly greater than 0 also. X is the element of dt implies that Tx is the element of y and capital Y is a norm space. And as capital Y is a norm space, therefore here we have Tx satisfy this first axiom, and therefore we have norm of Tx, it is always greater than or equals to 0. Now it is true for any x belongs to dt. That means it is true for all x belongs to dt minus singleton 0. As it is true for any x belongs to dt minus singleton 0, therefore it is true for the supremum also, and therefore we can write down supremum of norm of Tx divided by norm of x, because norm of x is strictly greater than 0, and therefore we can take supremum over x belongs to dt, x not equals to 0, norm of Tx divided by norm of x, it is greater than or equals to 0. And as it is true for supremum, but that supremum is nothing but our norm of T, and therefore here we write down that is norm of T, it is greater than or equals to 0. We start with the non-zero element of capital X, and here we get that its norm is strictly greater than 0, but x is the element of dt implies that Tx is the element of y, and y is a norm space, and therefore here we have norm of Tx, it is greater than or equals to 0. And now it is true for any x which is the element of dt minus singleton 0. As it is true for any x belongs to dt minus singleton 0, therefore it is true for supremum, and therefore we can write down that the supremum over x belongs to dt, x not equals to 0, norm of Tx divided by norm of x, it is greater than or equals to 0, but it is nothing but norm of T, it is greater than or equals to 0, and therefore the first axiom of a norm is satisfied. Now we come to the second axiom. In the second axiom, we have to show that N2. The N2, in that we have to show that norm of t equals to 0 if and only if t equals to 0. So we start with norm of t equals to 0. Norm of t equals to 0 if and only if we just write down the definition of norm of t, that is equals to supremum over x belongs to dt, x not equals to 0, norm of tx divided by norm of x, that is equals to 0. Now this supremum equals to 0, and in this supremum we know that x is not equals to 0. As x is not equals to 0, x not equals to 0 implies that norm of x, that is also not equals to 0. And therefore here when we say that this supremum equals to 0, if and only if supremum is 0, it is possible only when norm of tx, each term must be 0. But again here x not equals to 0, therefore it is not equals to 0, and therefore norm of tx divided by norm of x equals to 0 if and only if norm of tx equals to 0, and it is true for all x belongs to dt with x not equals to 0. It is also true for all x belongs to dt minus singleton 0. If and only if now norm of tx, this is the norm on y, and y is a norm space, therefore norm of tx equals to 0 if and only if tx equals to 0 for all x belongs to dt minus singleton 0. As it is true for every x belongs to dt minus singleton 0, that means images of all the points of dt minus singleton 0 equals to 0, it is possible only when the operator equals to 0, and therefore if and only if t equals to 0. We start with that norm of t equals to 0 and we get that t equals to 0, and therefore the second axiom of a norm is satisfied. Now we have to prove the third axiom, that is norm of alpha t equals to mod alpha into norm of t, that is we have to show. We have to show that norm of alpha t equals to mod alpha into norm of t, where alpha be any scalar. So to prove this, here we use the alternative formula for the norm of t. Consider norm of alpha t, that is equals to supremum over x belongs to dt, norm of x equals to 1, norm of alpha t of x, that is the norm of alpha t of x. Now this is equals to supremum over x belongs to dt, norm of x equals to 1, norm of alpha into tx. Now here this is scalar, and tx, it is the element of capital Y, and capital Y is a norm space, and therefore norm of alpha tx, it is written as supremum over x belongs to dt, norm of x equals to 1, we can write it as mod alpha into norm of tx. Now this alpha is independent of this supremum because this supremum is taken over x, and this alpha is independent of this x, and therefore it is written as mod alpha into supremum over x belongs to dt, norm of x equals to 1, norm of tx, and it is equals to mod alpha into norm of t. That means norm of alpha t, it is equals to mod alpha into norm of t. In this way, the third axiom of a norm is satisfied. Now we have to prove the last axiom of a norm, that is the triangle inequalities. So for this, here we take the two bounded linear operator. We take let T1, T2 be any two bounded linear operator. Bounded linear operator. They are again from the script d of t to 1. Be any two bounded linear operator. Then we have to show that. Norm of T1 plus T2. In the same way, we have to show that it is less than or equals to norm of T1 plus norm of T2. That is we have to show. So we start with this. Consider norm of T1 plus T2. Again we apply here the alternative formula, that is supremum over x belongs to dt. Norm of x equals to 1. Norm of T1 plus T2 of x. It is equals to supremum over x belongs to dt. Norm of x equals to 1. Norm of T1x plus T2x. That is norm of T1 plus T2. That is equals to supremum over x belongs to dt. Norm of x equals to 1. Norm of T1x plus T2x. As x belongs to dt, norm of x equals to 1 implies that T1x, T2x both are the elements of y, and capital Y is a norm space. Therefore, as capital Y is a norm space and T1x, T2x both are the elements of capital Y, and therefore norm of T1x plus T2x, that is always less than or equals to norm of T1x plus norm of T2x, and it is true for all x belongs to dt. As it is true for all x belongs to dt, therefore it is true for supremum also, and therefore we can write down therefore it is less than or equals to supremum over x belongs to dt. Norm of x equals to 1. Norm of T1x plus supremum over x belongs to dt. Norm of x equals to 1. Norm of T2x. And that is equals to norm of T1 plus norm of T2. That means norm of T1 plus T2, it is less than or equals to norm of T1 plus norm of T2. In this way, the fourth axiom of a norm is satisfied, and therefore the norm defined like this: norm of T equals to the supremum over x belongs to dt, x not equals to 0, norm of Tx divided by norm of x satisfy all the axioms of a norm, and therefore it is a norm, and hence in this way we prove the lemma about the bounded linear operator.